Hey everybody, today we're going to go over one of my favorite lessons of the year. It's too bad I couldn't be there for you. But we're going to talk about exponential growth and exponential decay and how it relates to real life. In class a few days ago, I talked about the difference between investing, like taking some money, putting it aside, and having it grow because of a good investment, and decay, which would be like when you have a car and the car goes down in value. So today we're actually going to write the functions out. We're going to calculate the values, and we're going to go from there. So if you want to fill in the blanks really quick, we've got exponential growth models, which look like this, and then eventually we're going to get to the decay models. Now, I have actually heard these. A simpler way of thinking about it is just you have A times B to the X. A is your starting amount. Whatever value you started with was A. And then your growth factor is going to be B, which I'll actually fill in the blanks right now here. And if none of this makes sense right this second, I think it'll make a lot more sense when we start working through it. And then just that little r there in the formula that they give you. So again, we've got kind of two ways of looking at it. We've got the formula they wrote down for you, and then we've got the simplified version. The benefit of using theirs is that you can consider that r the growth rate. So here's what's going on. Let's use this first example using guitars to introduce the idea. So Tony purchased a rare guitar in 2000 for $12,000, and experts estimated that its value will increase by 14% per year. So if you want to make a prediction about what's going to happen, you start with the starting amount, which is $12,000. And then you have to figure out the growth rate. Now, the formula always has a 1 because 1 is how you keep your starting value. So for instance, if you take 12,000 and multiply by 1, you get 12,000. So that's not really a shocker to anybody. It's the number after it that determines whether or not your value is going to go up or down. So like if you were to put a 0.14 after that number, then you would end up getting a growth of 14%. So again, one of the biggest keys to getting this section right is remembering how decimals and percents work, remembering that 14% is 0.14. And then all you have to do from there is put a little exponent right here. Now, when we use our calculators, we're going to use an X. When we graph, we're not going to use a T in that spot. We're just going to use an X in that spot instead, because the calculator isn't really going to understand the difference. But anyway, so this would be the kind of thing that if you were on Desmos or if you were on a graphing calculator, you could punch that in. Now, I'm going to use the graphing calculator again because nobody can ever really tell you no as far as these graphing calculators are concerned. There's something you can use, SAT, ACT, all of the above, pretty much for the rest of your existence. Okay? And again, like I said, I'm going to put X instead of T because the calculator isn't really going to understand the difference. Now, the X value represents the number of years. So I'm going to go with 30 years. Why not? I'm just making this up as I go along. And then the value of the guitar, we're hoping that the guitar will eventually be worth $60,000. So we're going to make our window maybe up to $75,000 so that we can watch it work. And here we go. So there's the value of the guitar. It is going up, it is going up, it is going up, it is going up. And one cool thing you can do with these calculators, I mean, we've already talked about the table. And we've already talked about how on these calculators you can go through and you can follow along on the table. And in this case, you could just look and see how many years it's going to take to get there. Looks like it's something between 12 and 13 years is how long it's going to take to get to that amount. But another thing that these calculators can do, which is actually pretty cool, you could just, in the next graph, just type in the number 60,000. and it will graph a vertical line at 60,000. And then all you have to do is have the calculator figure out exactly where they cross. Now, for the calculator to do it, you have to hit second and then calculate right up here. It was a blue word, that's why I had to hit the blue button first. And intersect, because we want to see where they cross. I'm going to hit enter like 3 times. And I had said between 12 and 13 was my prediction, and sure enough, about 12.3 years. Was how long it took for the guitar to be worth 60 grand. Now, I don't know enough about guitars to know what kind of guitars will be worth 60 grand eventually, but that sounds like a good deal. All right, now, let's write a new function, but let's use the other guitar. So if you look at the next problem, it says, well, there was another one out there that was worth 15,000. But the experts think it's not going to go up in value by quite as much. Now, one of the things that people get wrong all the time is they don't realize 9% is not 0.9. 9% is 0.09. So be very careful when you're crafting these equations, okay? Now, what I'm going to do, I'm going to go back into the graph. I'll slide it over here so you can keep looking at that. And I'm going to compare the two graphs to each other. So I'm going to leave the first one in there. But now I'm going to take the second graph and put it next to it. Now, again, we're going to put X right there. And some of you are like, well, why wouldn't you just put 1.14 or 1.09? It doesn't matter. You could. It would make no difference. It says in the question, determine after how many years the guitars will be worth the same amount. So the second guitar was worth more in the beginning. However, it is not gaining value as quickly. So what we're thinking is maybe the second one will start higher, but then it won't go up as fast. So let's take a quick look and see if the graph shows that. Okay, so here's the first one. It's growing, okay, pretty well. Now the second one is going to start a little bit higher. Yeah, it doesn't go up nearly as fast. So after how many years will the two guitars be worth the same amount? So once again, this is something you could research in the table, and you could eventually find out as you go through. It does not take very long for the first one to pass the second one. It only takes about 5 years. But once again, remember, these calculators have a special feature where you can just calculate where they cross. So I'm going to do that, and I'm going to find out it was, drum roll please, yep, 4.98 years. Which wasn't much of a surprise after looking at the table. All right, now, we did a growth model. Now we are going to do a decay model. And if I go too fast at any point, you can just pause your video. So now we're talking about a decay factor because your amount is going down over time. And then, of course, that would make that a decay rate. And now, like I said before, the best example of this is when we get into cars. Whenever we're dealing with cars, we're pretty much assuming that the value is going to go down over time. So what's going to happen is now we're still going to have a starting amount. I don't know if you noticed that, but all of these problems, they start with the starting amount. And they also have a 1 inside the parentheses for your starting value, because if you multiply something by 1, the number stays the same. So we want to keep that starting value, but then we want to start taking away from it. Now, one big key to this problem, remember what we talked about before, 9.5% as a decimal is actually 0.095. You always have to move the decimal over twice, And if you have an extra spot, you need to put a 0 as a placeholder. So it's one of those old school things that you might not remember all that well, but you need to make sure you get good at it, or else you're going to make some mistakes. All right, so once again, in the model, we normally use the letter t as your exponent, but when we are graphing, we will normally use x because the calculator doesn't really know the difference. So that's what we're going to do. We're going to do 28,000. Hang on, let me get rid of the initial. There you go. There you go. All right, so 28,000. But now the biggest key is, since it's exponential decay, you're going to want to do a minus instead of a plus. So 1 minus 0.095. And then we go to the x power. I think my window is going to be pretty much good to go. It's never going to make it up to 75,000 though, because this thing is going down in value. In fact, it's never going to go above the initial value. So if I start at 30,000, that's probably a pretty good indicator. Now, if you ever got a question, that just said how much would it be worth after 5 years or something like that, it would be really easy, because you could just take this, you could take the info, and you could just take the 1 minus 0.095, and you could just put a 5 in for the years. So there you go. After 5 years, it's already down to like 17 grand. So that is something that can be done sometimes, but we're just practicing our graphing and our modeling here. Now in this example, they're asking us when it's going to be worth $5,000, so we're going to go in here. We're going to put 5,000 in the second line, and we're just going to see where this graph did this. Now, the example I used for my car, and we're going to go back and we're going to do the intersecting thing just like we did the other times. If you don't have a graphing calculator on you, Desmos will do the same thing. It actually does it a little bit faster, but again, I'm just a little worried about when you're going to be able to use it and if you're going to be able to use it on the unit test. In our car example, my car depreciated very quickly. Trucks usually don't depreciate quite as quickly, but they still do go down in value. So here you go after 17 years. So 17.26 years. Okay, there you go. That was when the value of the truck was $5,000. All right, now, once again, I kind of like this next example here, because now you got a sports car, and so it's going to start with a higher value, but it's also going to go down faster. And the reason it's going to go down faster is because, quite simply, it's a sports car. And if it is a sports car, it's not going to hold as much value as quickly. You know, a truck is oftentimes there to serve a purpose, whereas a sports car is there to look good, and the older it gets, the less good it's going to look. So now I'm going to compare these two. So it's going to start higher, and I'm not even going to bother changing my window at this point. I'm actually just going to leave it here, and I'm just going to see where they cross, because I know they're going to cross at some point. And again, on Desmos or on your TI graphing calculator, either one, make sure you're using X instead of T. So here's the truck, started at 30 grand, and now it's going down in value over time. Very slowly. And then you've got the sports car. Now the sports car was off the graph to begin with, but as you can see, when you depreciate faster, your value starts going down way, way faster. So we're going to calculate the intersection point right here. And it turns out they crossed after 7.57 years. There you go, 7.57 years. All right, so I hope that helps you get going. You've got a few problems on the back that you need to practice for yourself. And then if you look in your packet on the 6.3, there is some more work as it relates to growth and decay. So use your calculators, make sure you use your tech, and we'll see how it goes. Thanks for watching.